All right, in this video, what we're going to do is we're going to look at deriving on a very simple model what our best estimates would be. Now, this is similar to maximum likelihood estimation that we did in week 5, but we're going to have a different criterion that we're trying to optimize. In fact, if we do model this using some normal distribution ideas, it is actually the exact same as the maximum likelihood approach. But for now, we're going to use a different criterion that we've talked about in the earlier videos of least squares regression. Now, I'm going to start with a very simple model, the most simple model that we discussed in the video. I'm going to say that y is simply beta plus epsilon, where beta is essentially just some number. I want to pick what the best number for beta is with some error. And I want to say, well, what is best? How do I determine best? Well, I want to find what number is basically as close to all the values of yi as possible. So if I just say I want to give you the best amount of how much beer is sold at Ohio State football games across game. I can say I have all my data, but I say, well, what's my best guess? Now, I think you can probably intuit, if you had to give one number as a guess, you'd probably just say, well, it's probably just the average of all the different values. And we're going to see that that's true. But let's try to think about this from a modeling context. We know that the value of how much beer is being sold is really some number, some best number, plus an error. But what is that best number? And from least squares, we want to say that the epsilon, the error, is yi minus beta. And my goal is I want to minimize the sum of the squared errors. That was my goal. So I want to minimize the sum of yi's minus beta squared. Now, I want to find out what value of beta minimizes that. Well, we've talked about that with likelihood estimation as well, is all we have to do is take the derivative, set it equal to 0. And this is the very, very simplistic function. So I take the derivative, I get, let's see, so derivative of, we'll call this SSE, which we're going to see pop up quite a bit. SSE stands for sum of squared errors. So we're going to take the derivative with respect to beta, and that's simply going to give me 2 times the sum of yi minus beta. And just like we did with likelihood estimation, this is just a constant. The beta is just a constant. We'd end up with 2 times the sum of yi minus 2 times the sum of beta. I'm writing that out in a almost painfully extra notation. Beta is simply a constant. When I sum up beta n times, I end up with 2 times the sum of yi minus 2n beta. So now I want to set that equal to 0. Set it equal to 0. I get 2 times, in fact, I'll leave it like it is. 2 times the sum of yi minus 2n beta hat equals 0. I can divide both sides by 2, and since it's 0, it's no problem. I end up with yi equals n times beta, and lo and behold, the most likely value of beta, the best value, the value that minimizes these error terms over here, is x bar. Now, I apologize, should be, not x bar, we're dealing with y's. The best value of beta is y bar. So if you tell me the best value that minimizes the sum of squared errors with this simple model, it's y bar. Now the next most likely question is, well, what if we have additional factors? So I want to estimate the amount of beer sold at the stadium, and now I know the temperature of the game. How can I update my model? This is too easy. This is too simple. It doesn't take care of the temperature of the game. Let's take an example where we look at extending this using outside information.